going to talk about fat metabolism. And I tend to think fat metabolism is just a little bit more straightforward. Now, fats come in all different types within the body, whether you can ingest it and how it's stored. But specifically, the fat that we can utilize for energy are going to be our triglycerides. As review, we've got a picture of a triglyceride on this slide. It's composed of a glycerol molecule and 3 fatty acid chains. And we're going to separate that glycerol molecule, and then we're going to metabolize those fatty acid chains in order to generate very high amounts of ATP. Now, the process of breaking apart these fatty acid chains is called lipolysis, and that's supported by an enzyme called lipase. Now, I've alluded to this already, but the rate of fatty acid metabolism is actually going to depend on how much free fatty acids we have available. So remember that concept called the mass action effect? The more substrate you have available, the more it's going to facilitate that type of metabolism. So the more free fatty acids you have available, the more free fatty acid metabolism you'll undergo. One of the benefits of training that we're going to talk about later in the semester is that your body, just through training, will adapt to utilize free fatty acids a little bit more effectively and a little bit more quickly so that you can generate these high amounts of ATP. Now, despite being slower than glucose metabolism because of the different steps involved, it is well worth it to metabolize our fat molecules. We get anywhere from 3 to 4-fold more ATP when we metabolize a fat molecule compared to a carbohydrate molecule. So where we're looking at for carbs 33 to 32 ATP, we're sometimes looking in the hundreds of ATP when we metabolize different free fatty acids. And I'll show you that the number is dependent on how long that free fatty acid chain is actually going to be. The process of breaking down our free fatty acids so that they can be metabolized starts with beta oxidation. And if you're doing a comparison between carbohydrate metabolism and fat metabolism, carbohydrate metabolism starts with glycolysis before entering the Krebs cycle. Fat metabolism will start with beta oxidation before entering the Krebs cycle. So the process of converting those free fatty acids to acetyl-CoA before they're going to enter the Krebs cycle is what's called beta oxidation. This is going to require us to put a little bit of energy in. No different than when we went through glycolysis, we put 2 ATP into that process, and we're going to do the same thing here with beta oxidation. Now, unlike with carbohydrate metabolism, where the number of carbons is always the same, so we're always able to estimate the number of ATP exactly, with a fat molecule, it's going to be dependent on the number of carbons, which is variable between each fat molecule. So in this case, the example is a 16-carbon free fatty acid, and it's going to yield 8 acetyl-CoA molecules after it goes through beta oxidation. This is compared to 1 glucose molecule that will only yield 2 acetyl-CoAs. So you can see already that we're going to have more substrate that's going to enter into the Krebs cycle, which means we're going to end up with much higher overall ATP yields. Now, because fat relies on oxygen or aerobic metabolism, it's going to require a lot of oxygen to process all that ATP that it's going to be able to generate. Now, we've mentioned that the process of beta oxidation is taking this very long fatty acid chain, and we want to break the carbons so that we're creating 2 carbon molecules that are called acetyl-CoA molecules. It takes 3 steps to go through the process of beta oxidation. And in those 3 steps that are outlined in this slide, we produce 1 FADH molecule and we produce 1 NADH molecule. Just like you saw previously with carbohydrate metabolism, we're able to take those transport molecules that are carrying those extra hydrogens and thereby electrons and process them in the electron transport chain for energy. So in this case, that 1 FADH molecule provides 1.5 ATP, and that 1 NADH molecule provides 2.5 ATP. So that means for every bond that is broken during beta oxidation, we produce 4 ATP molecules. So in our example, we had a 16-carbon molecule. That means we're going to have to break 7 bonds because it's a linear chain. So we'll end up with 28 ATP. So that's 4 times 7 is 28 ATP total. So my first mathematical hint for you for beta oxidation, or just fat metabolism overall, is when you're trying to calculate the number of acetyl-CoA molecules that you'll have for any given free fatty acid that you're going to metabolize, you take the number of carbons in the molecule, so in this case it was a 16 carbon molecule for palmitic acid, and you divide by 2. And that's going to tell you how many acetyl-CoA molecules that you're going to have. When you need to know how many bonds you have to break in order to generate those acetyl-CoA molecules, you take the number of acetyl-CoA molecules that you're going to generate and you subtract 1, and that will give you 7 bonds that you'll have to break in this case. Now, the great part about learning about fat metabolism is that if you've already learned about carbohydrate metabolism, it makes the rest of the process very easy. So we've taken this long free fatty acid chain and we've done the first step, which is beta oxidation. So breaking that long chain into smaller 2-carbon molecules called acetyl-CoA molecules. Now these acetyl-CoA molecules are going to go into the Krebs cycle in the same way that we would put them into the Krebs cycle if they were a carbohydrate. The difference is with carbohydrates, we had 2 acetyl-CoA molecules, and with fat metabolism in this specific example, we have 8 acetyl-CoA molecules. So if we take our products by going around the Krebs cycle 1 time, we end up with 3 NADH molecules, 1 FADH molecule, and 1 GTP molecule. So we're going to multiply that by 8 because we're going to go around the Krebs cycle 8 times. So we'll have 24 NADH molecules, 8 FADH molecules, and 8 GTP molecules. Next, we're going to take those intermediate molecules and we're going to shuttle them to the electron transport chain. And this is going to allow us to generate ATP. And so we'll end up with 24 NADH molecules times 2.5. So we'll get 60 ATP plus 8 FADH molecules times 1.5. So we'll get 12 ATP. That's where you see the 72 on the table. And then those direct 8 GTP molecules will be immediately converted to 8 ATP molecules. So as you can see in this example, we had to put 2 ATP in. We generated 28 ATP during beta oxidation, and then we generated, in this case, an additional 72 ATP plus the 8 direct ATP to give us a total of 106 ATP. So if you could follow my math with that previous example and what was going on, fantastic. But I also appreciate that this is a bit abstract for some of you, and a visual might be helpful for understanding how we're breaking apart our free fatty acid molecule during beta oxidation and where some of these numbers are coming from. So this next information is exactly the same as what I've previously presented to you in this lecture. It's just using a different visualization to be able to see that. So in this example, we're going to again use palmitic acid, which is a 16 carbon acid. If you count across in this figure, you'll count 16 carbon molecules, and this is the actual structure of palmitic acid. So the first step is that we have to put 2 ATP into the molecule. So you put a little bit of energy in order to get a lot of energy out. And this is going to allow us to prime our molecule. Next, we're going to want to form acetyl-CoA molecules. An acetyl-CoA molecule has 2 carbons, so we're going to need to break our palmitic acid molecule into 8 individual 2-carbon molecules. So in order to do that, we need to break 7 bonds. So breaking those bonds is the actual action of beta oxidation. So if you remember from previously, every time we break a bond during beta oxidation, we get 1 FADH molecule and 1 NADH molecule. So that's going to give us a total of 4 ATP for every bond that is broken. In this case, we're breaking 7 bonds, so we're going to generate the 28 ATP in this step. Remember, the shorthand to get here was to take our 16 divided by 2, that gives you 8 acetyl-CoA, minus 1, that gives you 7. That means 7 times you're going to go through beta oxidation. So next we're going to take our 8 acetyl-CoA molecules and we're going to put them into the Krebs cycle. So remember, with each turn of the Krebs cycle, we'll get 3 NADH molecules, 1 FADH molecule, and 1 GTP molecule. So I showed you math on how to do that in the previous section. I'm just going to show you another way that you could go through the order of that math. So for 1 acetyl-CoA molecule, you'll get 3 NADH molecules. And so you multiply that by 2.5, that's 7.5 ATP. You'll get that 1 FADH molecule multiplied by 1.5, you'll get 1.5 ATP. Keep in mind we're using those multipliers because when we shuttle those molecules to the electron transport chain, that's how many ATP we'll be able to generate from those molecules. So that means we get 9 ATP molecules per Krebs cycle turn via oxidative phosphorylation. So they've got to make it into the inner membrane of the mitochondria to be phosphorylized to generate that ATP. Don't forget, we also get 1 direct ATP from that GTP molecule. So another way you could look at it is with each turn of the Krebs cycle, we're generating 10 ATP molecules. So in this case, that would give us 80 ATP molecules total. So if you take the 72 that you get from the NADH and the FADH and you add the 8 that you get directly from the GTP, that amounts to 80 ATP molecules. So exact same thing as we did in the previous example. It's just showing another way to add up those numbers. Now, one of the things that we didn't mention about the Krebs cycle earlier when we talked about it in terms of carbohydrate metabolism is how it's controlled through negative feedback. And similar to glycolysis that has a rate-limiting enzyme, PFK, that controls the speed of that reaction, the Krebs cycle also works the same way, except its rate-limiting enzyme is isocitrate dehydrogenase. And this enzyme occurs pretty early in the pathway, and it regulates how fast that pathway is going to move. So if there's a high amount of ATP available, it'll move more slowly. If there's a high amount of ADP, the low energy state, available, it'll speed up metabolism in this case.